Okay, in this video we're going to be talking about changes in state. And at first glance this might seem like a simple topic, but I'll tell you now it's going to be a little challenging probably. So changing in state would be, well, going from solid to liquid to gas. And you've probably learned this a bit in 6th grade, or maybe in another grade. But we're going to look at it from a weather perspective, which is going to be a little different. So, of course, we have evaporation. And evaporation would be liquid changing to a gas. You probably know that without a problem. So liquid to gas. And we know that we have liquid water, liquid H2O, going to water vapor H2O. So we're going from liquid to gas, and this is, of course, why if you leave a cup of water out after a few days, it seems to go away. Well, it requires heat energy to convert that water into gas. And if we look at the reference table, so take a minute to get your reference table out. You might want to pause the video. And here's my reference table here. There's a chart here that tells you how much energy it takes to go between states of matter. So to do evaporation, which is vaporization, which would be boiling or evaporation. Boiling is basically just rapid evaporation because we're really heating things up. We're looking at a temperature of 2,200, we're looking at what's called 2,260 joules per gram. So let's talk about that for a minute. So it requires 2,260 joules of energy per gram of material, or water in this case, to convert it to convert 1 gram of liquid water to gas. So a joule is a way of measuring energy, and we can use joules to measure heat energy. We can use joules to measure chemical energy, like in batteries, or in a chemical reaction. We can use joules of energy to measure, well, any form of energy, even stretching a rubber band or jumping up and down. But in this case, we're using joules of energy as a way of measuring how much energy it takes to convert, how much heat energy it takes to convert 1 gram of water from liquid to gas. Now, evaporation is considered to be a cooling process because it absorbs heat from the environment. Well, in this case, environment, we mean surroundings. So in order for evaporation to take place, we're going to be pulling heat into the water, warming it, causing evaporation. Now you might be thinking, well, why isn't it a heating process then? Because if we're putting heat into it, wouldn't it be a heating process? But I like to think about the example of a shower on a hot day. We talked about this example once before. If it's a really hot day, like a heat wave, and you take a shower, when you get out of the shower, no matter how hot it is, it might be 95, even 100 degrees outside. Well, as soon as you step out of the shower or out of the pool or out of the water in any way, you're going to feel cool at first. The water is evaporating off your skin. It's the same process as sweating. And when that evaporation happens, it's absorbing heat from the surroundings, which would include your body and the air around your body, and cool those areas down. So evaporation is a cooling process. We're thinking about the environment around the water. So we're not talking about the water itself. The water is gaining heat and warming and evaporating. But we're talking about what's happening to the environment around the water. In this case, the example of the shower, it would be your body. Your body is getting cooler because you're giving up heat to the water to cause evaporation. That's a complicated idea. Different way of thinking about it. If we look at condensation, well, condensation is, of course, the opposite. So now we're going from water vapor to liquid water We see this in the form of dew in the environment outside. We see this in clouds. Clouds are condensation. Dew is a form of condensation. And in this case now, water molecules release energy equivalent to what was absorbed during evaporation. So if we had 2,260 joules of energy per gram of water being absorbed, well, we're going to be releasing the same amount when condensation takes place. Condensation in the atmosphere results in the formation of clouds, dew, fog, and I'm going to add in here, it's a warming process. Because now we have to add heat from the environment. Let me scratch that. We are adding heat to the environment, but it's more like we're pulling heat out of the water. And if we're pulling heat out of the water vapor, we're adding heat to the environment. And we're causing heating around the cloud. When condensation takes place, we have this heating effect. So it's the opposite. When you get out of the shower, we have this cooling down. When we have condensation take place, water vapor to liquid water, we have a warming effect. So condensation is actually a warming process. It's warming the environment around the object. When a cloud forms, we have a warming process within the cloud as the water vapor is transitioning to liquid. So again, you have to kind of, get out of this mindset of like, well, we're adding heat to the water to cause evaporation, so it's a warming process. It's the other way around. If we're adding heat, it means we're taking heat away from the environment, causing it to be a cooling process. So it's a different way of thinking about it. This is a weather-oriented way of thinking about changes in state. It's a little different than what you're used to. If we look at melting, well, we're obviously going from solid to liquid. We're taking something like an ice cube and we're melting it. If we look at our reference table again, we can see how much energy that takes. And melting requires 334 joules per gram. And also, while we're looking at this, notice that melting and freezing both require the same amount of energy. In the case of melting, we're adding heat into the ice, 334 joules per gram. In the case of freezing, we're releasing the heat to the environment, but it's the same amount of energy. And the same with evaporation or vaporization and condensation, the energy is the same. It's just a matter of which way is it going. Is it going into the water or out of the water? So if we go back to melting, we're going from a solid to a liquid, of course. And it required 334 joules of energy per gram to convert ice let's look at something. It requires 344 joules per gram of energy to convert, let's just change this, 1 gram of ice to liquid water. Melting is a warming process. No, sorry guys, I wrote the wrong thing. Melting is a cooling process, rather. If you imagine having an ice cube in your hand, the heat from your hand goes into the ice. You melt the ice cube, but your hand feels cold. And that's what we mean by a cooling process. It's cooling the environment around the melting. And in this case, the environment is your hand. So your hand gets cooler when you hold the ice cube. You're losing heat. The heat from your hand is going into the ice cube, causing it to melt. We're cooling the environment around the ice cube. The heat is moving from your hand into the ice cube, cooling it down. Freezing is the opposite. So in this case now, water molecules or energy equivalent to what was absorbed during melting is going to be released. So now what we're doing is we're of course going from liquid to solid when we do freezing. And in this case, energy equivalent to what was absorbed during melting is released. So before we were putting heat into the ice, now we're taking heat out of the ice. And this is considered to be a warming process. Let's just skip this blank. So it's a warming process. It's 334 joules of energy per gram. So the energy is the same. It's just the direction. So now the heat is going out from the ice into the environment. We're taking water and we're pulling heat out to solidify it. Now, that might be a little confusing, but an example that I like to look at is oranges. And that might seem strange at first, but orange growers in Florida, in the southern states, will often spray water on their oranges when temperatures are forecast to get close to freezing or even below freezing. And they do this for a reason. They know that freezing is a warming process. And if they spray their oranges with water before a frost, or if the temperatures are going to get to like 31, 32, 30 degrees, they'll go out with hoses and they'll spray the oranges with water. And by doing that, when the water freezes, the heat from the water is coming out of the water into the orange and into the air, and adding just a little bit of heat energy to the orange, hopefully keeping it from freezing solid and ruining the crop. So it's a very clever way of keeping oranges warm because, realistically you can't heat an entire orange grove. That would be very difficult to do. But spraying water on oranges is very easy to do. And farmers can go out, they can spray water on the oranges. When the water freezes, heat from the water gets released as the water freezes. And this is why freezing is a warming process. And that's opposite the way you would usually think about this. But again, it's not about what the water is doing, it's what the environment around the water is doing. So as the water freezes, heat from the water is going into the orange and into the air around the orange, heating it just a little bit. And this little trick that farmers do, and here's this other picture of it, you can see the ice on the orange. This little trick that farmers do works well when the temperatures are forecast to just get a little bit below freezing, but not much. This wouldn't work in a climate like New York where temperatures are well below freezing. We can't do this when it's significantly below 30, like we often encounter here. But sometimes it gets a little cold in the south, and orange growers in the southern states will do this to keep their crop from getting ruined. So kind of an interesting idea. Now, this idea of freezing and warming processes is confusing. You might want to watch this video more than once if you need to, or at least the parts of it that you need to. Now, we talked about evaporation, condensation, melting, and freezing in this video. I'm going to do another video that's short, only a few minutes long, about two other phase changes, sublimation and deposition. Okay, so I'll post that in just a minute.